Hello and welcome back. In this video, we will be discussing how to find the correlation coefficient manually. If you had not watched the video on correlation, I recommend starting with that one. In that video, we talk about correlation R. In this video, we're going to talk about how we find our correlation coefficient. All right, let's start with some vocabulary. We got a bunch here. Correlation coefficient, a numerical measure of the strength and direction of a linear relationship between two quantitative variables. Remember, quantitative meaning numerical. Its value is always between -1 and +1. The Pearson correlation coefficient formula. The most commonly used correlation coefficient. It is calculated using a mathematical formula that compares how two variables vary together and is denoted by the symbol R. A quick comment, I know in another video I talked about residuals. I might have used R for residuals in that video. I don't quite remember off the top of my head, but I was thinking about that as I drafted this one. R is not the symbol we use for residuals. We just write the word out. R is the symbol that is associated with correlation coefficient. Okay? All right. Covariance, just to introduce it, we're not going to talk about it too much in this video, but this covariance is a measure of how two variables vary together. A positive covariance means the variables tend to increase together. A negative covariance means one variable tends to increase while the other decreases. And a covariance close to zero indicates no linear relationship or little linear relationship. Unlike correlation, covariance is not standardized, so it depends on the unit of measurement. So covariance is measured in some sort of units, inches, feet, centimeters, whatever. Linear relationship, a relationship in which two variables follow a pattern that can be reasonably represented by a straight line. As one variable changes, the other changes at an approximately constant rate. This constant rate part is important for the linear parts. That means it makes a straight line. Positive correlation, a linear relationship in which both variables tend to increase or decrease together. The correlation coefficient is positive, meaning R is greater than 0. Negative correlation, a linear relationship in which one variable tends to increase as the other one decreases. The correlation coefficient is negative, R is less than 0. Strong correlation, a relationship where the data points lie close together in a straight line, resulting in a correlation coefficient closer to -1 or +1. So like negative 0.95 or positive 0.9, that would be a strong correlation. I give some closer, better examples over here, but weak correlation. A relationship where the data points are widely scattered around a straight line, resulting in a correlation coefficient close to 0. I think in my linear regression video, I give visual examples of this, but as a recap, if the correlation coefficient is ±1, it's a perfect correlation. If it is somewhere between ±7 and plus or minus zero point 0.7 and plus or minus 0.9, so like negative 0.7 to negative 0.9 or positive 0.7 to positive 0.9, that would be considered strong. And then likewise, positive 0.3 to positive 0.7 or negative 0.3 to negative 0.7 would be moderate, and positive 0.1 to positive 0.3 or negative 0.1 to negative 0.3, that would be considered weak. And lastly, we have summation. We've gone over this a bunch. This is just a reminder. Summation is the Greek letter sigma. It indicates that a set of values should be added together. So some examples, if we see like summation x sub I, sum all the x values, summation y sub I, sum all the y values, summation x sub I squared, sum of the squared x values. So that means square all the x's, then add them up. Summation of x sub I, y sub I, sum of the products of each corresponding x and y value. So that means multiply x and y, all the x and y's, and then whatever those products are, add all those up. And then I like to use the sub I notation. You don't always see this, but just so you know what I'm talking about, it denotes each particular x or y value. So the sub I lets the reader know there's multiple x's or multiple y's, and that's why I like to use it. I think it's just a little bit more clear. So just to give a quick example of that, if we have a data set that looks like this, you could see in red, I put each value corresponds to the I value. So the first one is I equals 1. The second value 4 is I equals 2. Third value 8, I equals 3. Fourth value 3, I equals 4. Fifth value 2, I equals 5. And sixth value 6, I equals 6. Okay. All right. Now that we got the vocab out of the way, let's dive in. So we're going to be talking a lot about the Pearson correlation formula. Um, Similar to the least squares regression line, this is another equation that looks daunting as first, but we're going to break it up and make it real easy to work with. So here's our equation here. I'm not going to read all that, but I'm sure you could see it on the screen. And then where n is the number of observations or elements, sigma, summation, sum of, x sub I are the x values, y sub I is the y values, and we have down here in the denominator, I don't know if it's super obvious there, but we have a square root of this whole thing. So just a reminder, this is the square root symbol, and what? The square root is the inverse of an exponent. I guess you could say it's a number divided by itself or divided into itself. All right, anywho, let's take a look at this equation and see how it applies. Here we have our example. So just 5 elements for each. Nothing daunting. X sub I, our X elements are 1, 2, 3, 4, 5, and Y sub I, our Y elements are 2, 3, 5, 4, 6. So there's 5 elements in each set, so we can immediately denote n equals 5. All right. Step 1, create columns. So in this equation here, we have summation of X sub I, Y sub I, summation of X sub I, summation of Y sub I, summation of x sub I squared, and summation of y sub I squared. So we want to calculate all those just so we can have them readily available to just plug right into this thing. Again, we already found n equals 5. So we're going to make, well, the x sub I and the y sub I are given to us in the problem. So we really just need to make 3 more columns. 3 more columns here, and just figure out the value. So the x sub I squared column, we take each value from the x sub I column and just square it. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. Similar enough, the y sub I squared column, we take each element from the y sub I column and square that. 2 squared is 4, 3 squared is 9, 5 squared is 25, 4 squared is 16, and 6 squared is 36. And then the x sub I, y sub I column, we take the product of each term in the x sub I and y sub I column and multiply the 2 rows. So 1 times 2 is 2, 2 times 3 is 6, 3 times 5 is 15, 4 times 4 is 16. Did I say 16? That's supposed to be 15. Anyway, 4 times 4 is 16, and 5 times 6 is 30. All right. Next step, compute the summation of each column. So I just added an extra row to the bottom of each column, and I just put it like, hey, this is our summations. Add up the x sub I column, we get 15. Add up the y sub I column, we get 20. Add up the x sub I squared column, we get 55. Add up the y sub I column, we get 90. And add up the x sub I times y sub I column, and we get 69. So I'm sure you noticed I have all of these values highlighted in different colors. I did that so that when we get to step 3, substitute each value into the Pearson equation, hopefully it makes it easier to see where the numbers came from. Okay, so n is 5 right here. Summation of x sub I, y sub I, highlighting that in blue, that's the sum of this column, 69, goes there, minus the products of summation x sub I and summation y sub I, the products of each 2 column, not the product of the summation. So the x sub I column gave us 15, the y sub I column gave us 20, that goes there. Then we focus on the denominator. Remember, this whole thing is in a square root. That's easy to forget. Hopefully we could see it there. I think I made it pretty obvious. And also, like I'm sure you noticed my use of brackets. When we have parentheses inside parentheses, my order is typically is, I forget what those are called, but then those, brackets, parentheses. So parentheses always go the inside most, brackets the middle one, and then the squiggly are the outside most, but we didn't need these for this example. All right, anyway, n again is 5. This is the summation of the x sub I squared column, which is 55. This one, you can see the square is outside the parentheses, so it's the summation of x sub I, and then that value squared. Here, n is 5. This is the summation of the y sub I column, which was 90, and then this is the summation of the y sub I column, and then that value squared, so we get 20 squared here. And then we just, from here, once everything's in, as long as you put this in a calculator correctly, just a quick plug, I highly recommend, can you see it on here? Yeah, what is this? The Casio FX 115 ES Plus. I love this calculator, mainly because the calculator has a fractions button, and I can literally just put this entire thing, and as long as I type it correctly, I could just plug it in and do it in one step. You can do it with the TI-84, but it's much simpler. This is also cheap. This thing's like 15 bucks. But when I was a student, I would carry around literally this calculator and a TI-84 just because this is easier for regular calculations, where the TI-84 you need for graphing and tests and whatnot. Anyway, calculator plug there. We go through this, simplify it, and we should get R equals 0.900. Cool. So what does this mean? Let's interpret this. So first we determine whether R is positive or negative. We could see clearly here it's positive. Describe the strength of the linear relationship. So I had that written out over here. It's in this range of plus 0.7 to plus 0.9. We got exactly plus 0.9. So we can say it's strong and explain the result in context. This is more wordy than it needs to be, but at least it's crystal clear. We could say something like, the correlation coefficient is R equals 0.9000, which indicates a strong positive linear relationship between X and Y. This means that as the value of X increases, the value of Y also tends to increase. Because the correlation is strong, the data points lie relatively close to a straight line, making a linear model a reasonable way to describe the relationship. Cool. Some common mistakes that we're not going to make: forgetting to square X and Y before summing. This is a big one right here, mixing up summation of X of I squared with summation of X of I, and then that value squared. The square being on the inside of the parentheses or the outside makes a huge difference. Messing up our order of operations. Again, plug for the Casio FX115ES. If you use this calculator, it's very easy to make sure it's all correct. And rounding too early. My rule of thumb is I do not round until the very last step. If I'm working with, say somewhere in my calculation, I have 1/3. Okay, like plus 7 divided by 9 times the square root of 10, whatever. I'm going to keep this as 1/3 until I get to the very end. Honestly, I'd plug this whole thing into a calculator as opposed to writing 0.3 plus 7 over 9 times what's root 10. I just tried to pick something ugly off the top of my head. Root 10 is, it's a 3.16. So if you plug this into a calculator, you're going to get a different value than if you just leave it in this form and plug this into the calculator. So this would be the most precise answer you could get. Whereas with this, you've rounded this value and this value. And by rounding those values, it will skew your answer at the end and potentially make it incorrect. All right. Let's get rid of all this. All right. And here we have a practice problem. Find the correlation coefficient R of the given data and explain the result in context. Cool. So take a minute to take a stab at this problem, pause the video here, and take a look. All right. Hopefully you pause to work on it. Let's take a look at the solution. So you can see I immediately make a note, n equals 6, and we need our X sub I squared, Y sub I squared, and X sub I, Y sub I columns. Fill all that in and find the summation of the columns, get the values here. We should get values that look like this. Here is our Pearson equation. Plug each value into the Pearson equation and just start simplifying. I did all the work out for stuff like this. I like to show my steps. And then you could see here, like this is a good example. I did not round this square root because I knew this number was going to be ugly. So instead of rounding this, I just left it just like this when I plugged in my calculator, and we get R equals 0.995. You should get something close to that. And just an example, let's see what happens if you do round that, just out of curiosity. R equals 525 over, let's see, what's the square root of this bad boy? Square root of 278, 145. Yeah, so let's round it to 2 decimal places, and we get 527.39. Okay, so what does this equal now? 525 divided by 527.39, and we get, all right, well, not the best example because we still get 0.995. So in this particular example, it actually happened to work out. But still, take my word, like you don't want to round until the very last step because something might go wrong. So where's this? And all right, the interpretation, what does this all mean? So this is positive and it's between 0.9 and 1. So we could say it's a strong positive linear relationship between hours studied and quiz scores. As students study more hours, the quiz scores tend to increase, and a linear model would be appropriate for this data. Cool. That's everything I have for you on the topic of, what's this called again? I always forget what they're called. Correlation coefficient, how to find it manually. In the next video, I'll show you how to do it with a TI-84, but I think it's good to see how we do things manually first. Anywho, thank you for watching. As always, a link to the notes will be in the video description, and I will see y'all next time. Take care.